Compounds. A compound is a substance composed of two or more elements combined in a specific ratio and held together by chemical bonds. Familiar examples of compounds are water, H2O, and salt, sodium chloride. Lewis dot symbols. When an atom forms compounds, it is their valence electrons that actually interact. A Lewis dot symbol consists of the element's symbol with dots. Each dot represents a valence electron. So for example, boron, with an electron configuration of 1s2, 2s2, 2p1, has 3 valence electrons. We can draw the Lewis dot symbol as a B and 3 dots to symbolize the 3 valence electrons. It does not really matter where you put those electrons around the boron, as long as you do not pair them unless you need to with a different atom. Here are the Lewis dot symbols of the main group elements. You may notice that the pattern of dots is always the same as you go down the group, which makes sense because the groups are designated by the electron configurations, and therefore each element in a group should have the same number of valence electrons. So let's look at these further. So we have boron on the left with a 1s2, 2s2, 2p1. Move on to carbon, we have a 1s2, 2s2, 2p2. Notice that we have 4 dots around carbon. Once you reach 5 electrons in nitrogen, we have to start pairing these electrons, or dots, if we want to simplify. When you are filling these out, just remember they can only have 4 single electrons, after which you gotta start pairing up however many you have. Simple rules, well, for main group metals such as sodium, the number of dots is the number of electrons that are lost when they form ionic compounds. I'll learn about this in a second. And for non-metals in the second period, the number of unpaired dots is the number of bonds the atom can form. So as we see here, oxygen has 2 single electrons, therefore oxygen can form 2 bonds. Ions may also be represented by Lewis dot symbols. So if we start with the sodium with its 1 dot and we form sodium plus ion, we remove that valence electron, we end up with a core of 1s2, 2s2, 2p6, and as it's the core, we do not show any electrons. Remember, in the Lewis dot symbol, we only show valence electrons. Of course, do not forget the charge. For oxygen, on the other hand, oxygen can gain 2 electrons to become O2 minus. Well, at this point, we have to show all our valence electrons, even though we filled the new outer shell. And once again, don't forget the charge. Ionic compounds and bonding. Ionic bonding refers to the electrostatic attraction that holds oppositely charged ions together in an ionic compound. So, example here is that a sodium will want to lose an electron to become sodium plus. Chlorine wants to gain an electron to become Cl minus. And if we combine the two, we get sodium chloride, and the attraction between the cation and the anion draw them together, giving us sodium chloride. The resulting electrically neutral compound, sodium chloride, is represented with the chemical formula NaCl. The chemical formula, or simply formula, of an ionic compound denotes the constituent elements and the ratio in which they combine. A 3-dimensional array of oppositely charged ions is called a lattice. Lattice energy is the amount of energy required to convert a mole of ionic solid to its constituent ions in the gas phase. So here we see the process of lattice formation when a sodium atom donates an electron to the chlorine atom, so that you end up with a sodium ion and a chloride ion, and they combine in this 3D lattice of sodium chloride. The formation of ionic bonds releases a large amount of energy. If you think about it, you have loose particles that are in motion, and they have to all come to a standstill in a solid to release energy. The magnitude of lattice energy is a measure of an ionic compound's stability. Lattice energy depends on the magnitudes of the charge and on the distance between them. So once again, we use this equation of F is proportional to Q1 times Q2 over D squared, where Q is the amount of the charges and D is the distance that separates the two. Here are some examples of lattice energies of selected ionic compounds, and hopefully you will see a pattern emerging. If we keep the metal constant and start changing the anion, the halogen anion, we will notice that as the anions get bigger, the lattice energy decreases. And we can see that same pattern again and again. We also see that if we have a metal ion that has a higher charge, so magnesium is usually 2 plus versus the sodium 1 plus or potassium 1 plus, we see that the lattice energy increases dramatically. And this makes sense if you think about the magnitude. You are now multiplying charge with a 2 plus instead of a 1 plus. We also should probably comment on the melting point. Well, you may see a general trend emerging that as the lattice energy decreases, the melting point also decreases. Lattice energy depends on the magnitudes of the charge and on the distance between them. So everything we saw in the prior table makes sense. As our ions get bigger, the distance gets bigger and therefore the lattice energy decreases. Whilst as the charge increases, the lattice energy also increases. Naming ions and ionic compounds. A monatomic cation is named by adding the word ion to the name of the element. So potassium plus is a potassium ion. A monatomic anion is named by changing the ending of the element's name to "ide". So chlorine minus is a chloride. An oxygen 2 minus is an oxide. Some metals can form cations with more than one possible charge. So Fe2 plus would be the ferrous ion. Fe3 plus is the ferric ion. Mn2 plus is manganese 2 ion. Mn3 plus is manganese 3 ion. And Mn4 plus is manganese 4 ion. Notice the use of Roman numerals in this case. Also, why is iron ferrous and ferric? Well, because they've been known for such a long time that they have been granddaddied in the naming system. If you called it iron 2 and iron 3 ions, that would be fine. So here's a generic list of the cations you need to be familiar with and recognize by name. So you don't have to memorize all the names of the elements on the periodic table, but you have to know these ones. And of course, the most common ions that can form, shown here. And these are the most common anions you need to be familiar with. Formulas of ionic compounds. Ionic compounds are electronically neutral. In order for ionic compounds to be electronically neutral, the sum of the charges on the cation and anion in each formula must be 0. So for example, aluminum oxide. Aluminum has a charge of 3 plus, and oxygen has a charge of 2 minus. Therefore, you need 2 aluminums to give you 6 plus, and 3 oxygens, 6 minus, to cancel out. So our ionic formula is Al2O3. So how do we deal with this in conversation? Say I want to talk about aluminum oxide. How do I make sure that I'm talking about Al2O3 without having to say it constantly? Well, luckily there's a naming convention for this. We can follow this chart to figure out how to name our compounds. If the compound contains a metal and a non-metal, the compound is most likely ionic. We then have two options. If the metal cation has only one possible charge, such as alkali metal cations, alkaline earth metal cations, silver, aluminum, cadmium, and zinc, then the naming applies that you name metal first and add "ide" ending to the root of the non-metal name. So zinc chloride, aluminum oxide, sodium chloride. Because those ions only have one possible charge, we automatically know what the chemical formula should be. However, if the metal cation has more than one possible charge, any other metal as opposed to the ones on the left, then we got to name the metal first and then specify the charge of the metal cation with Roman numerals in parentheses, and then add I to the root of the non-metal name. So this would be something like iron 2 chloride or manganese 2 oxide. So just in writing now, to name ionic compounds, first you name the cation and omit the word ion. So when you have a potassium ion, it's just potassium. And then use a Roman numeral if the cation can have more than one charge, as mentioned earlier. And then finally name the anion and omit the word ion. So examples, NaBr is sodium bromide. FeCl2 is iron 2 chloride as opposed to FeCl3, which is iron 3 chloride. Covalent bonding and molecules. When compounds form between elements with similar properties, electrons are not transferred from one element to another, but instead are shared in order to give each atom a noble gas configuration. This approach is known as Lewis theory of bonding, named for its proponent, Gilbert Lewis. Lewis theory depicts bond formation in hydrogen gas as a hydrogen with a single Lewis dot combining with a hydrogen with another single Lewis dot to form two hydrogens with two dots in between them. This type of arrangement, where two atoms share a pair of electrons, is known as covalent bonding, and the shared pair of electrons constitutes a covalent bond. A molecule is a combination of at least two atoms in a specific arrangement held together by chemical forces, i.e. chemical bonds. A molecule may be an element or a compound. Different samples of given compound always contain the same element in the same ratio. This is known as the law of definite proportions. So just as an example, if we were to take 123 grams of carbon dioxide, there will be 89.4 grams of oxygen in it and 33.6 grams of carbon in it, giving you a ratio of 2.66 to 1. However, if we take 50.5 grams of carbon dioxide and we end up with a mass of 36.7 grams of oxygen and 13.8 grams of carbon, we still have the 2.66 to 1 ratio. If two elements can form two or more different compounds, the law of multiple proportions tells us that the ratio of masses of one element that combine with the fixed mass of the other element can be expressed in small whole numbers. In addition to carbon dioxide, carbon also combines with oxygen to form carbon monoxide. So we can look at this. 16.3 grams of carbon monoxide contains 9.31 grams of oxygen and 6.99 grams of carbon, giving you a ratio of 1.33 to 1 of oxygen to carbon. The mass ratio of oxygen to carbon in carbon dioxide is 2.66 to 1, and the ratio of oxygen to carbon in carbon monoxide is 1.33 to 1. The ratio of two such mass ratios can be expressed as a small whole number. So, if we take the mass ratio of oxygen to carbon in carbon dioxide and divide it by the mass ratio of oxygen to carbon in carbon monoxide, we end up with a 2 to 1 ratio, telling us that carbon dioxide has twice as many oxygens as carbon monoxide. So in other words, for every carbon in a molecule, there are two oxygens in carbon dioxide and only one oxygen in carbon monoxide. Diatomic molecules contain two atoms and may be either heteronuclear or homonuclear. Polyatomic molecules contain more than two atoms. So examples here, a homonuclear diatomic molecule could be something like hydrogen. Heteronuclear diatomic would be something like carbon monoxide. And polyatomic would be something like methane, CH4. As you will see lots of molecules shown Here's a summary of the colors often used in molecular art depicting different elements. So hydrogen is usually shown as white, carbon is usually black, nitrogen is blue, oxygen is red, chlorine is green, and so on and so forth. You do not have to memorize these, but just know that there is somewhat standardization on what colors are used for what elements. Molecular formulas. A chemical formula denotes the composition of the substance. A molecular formula shows the exact number of atoms of each element in a molecule. Some elements have two or more distinct forms known as allotropes. For example, oxygen, O2, and ozone, O3, are allotropes of oxygen. A structural formula shows not only the elemental composition but also the general arrangement. So, just to emphasize, a molecular formula would be H2O for water, whilst a structural formula would be an HOH because it's showing you how the atoms are arranged in this molecule. Empirical formulas. Molecular substances can also be represented using empirical formulas, the whole number ratio of elements. While the molecular formulas tell us the actual number of atoms, the true formula, the empirical formula gives you the simplest formula. So for example, if a molecule happened to be N2H4, the empirical formula would be NH2. The molecular and empirical formulas are often the same, but as seen in this example, they are not always. So here we have multiple compounds and the molecular formulas, models of what the molecules look like, and the empirical formulas for each molecule. You will notice that for some of them, the molecular model for the empirical formula looks similar to the molecular formula, but tends to be a little smaller. But if this is the case, it tends to be that the molecular model of the empirical formula is just the repeating unit throughout the actual model. Naming molecular compounds. Remember that binary molecular compounds are substances that consist of just two different elements. So nomenclature. First, we must name the first element that appears in the formula. Second, name the second element that appears in the formula, changing its ending to "ide." So for example, HCl is hydrogen chloride, and HI is hydrogen iodide. Greek prefixes are used to denote the number of atoms of each element present. So let's cover them. Mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, and deca for 10. So let's see those in action. Well, carbon monoxide, mono is 1, so monoxide is 1 oxygen. Carbon dioxide, there are 2 oxygens. Sulfur trioxide has 3 oxygens, and say dinitrogen pentoxide has 2 nitrogens and 5 oxygens. The prefix mono is generally omitted for the first element. Otherwise, carbon dioxide would be monocarbon dioxide. For ease of pronunciation, we usually eliminate the last letter of a prefix that ends in O or A when naming an oxide. So example, N2O5 is dinitrogen pentoxide, not dinitrogen pentaoxide. All in the purpose of simplification of pronunciation. Compounds containing hydrogen. The names of molecular compounds containing hydrogen do not usually conform to the systematic nomenclature guidelines. Many are called by the common, non-systematic names or by names that do not indicate explicitly the number of hydrogen atoms present. So for example, B2H6 is just diborane, SiH4 is silane, NH3 is ammonia, PH3 is phosphine, H2O is water, and H2S is hydrogen sulfide. Of course, we could name these with the systemic nomenclature. So water would be dihydrogen oxide, Ammonia would be nitrogen trihydride, and so on and so forth. But because these names are so common, we're better off using the ones that are being used. One definition of an acid is a substance that produces hydrogen ions when dissolved in water. HCl is an example of a binary compound that is an acid when dissolved in water. To name these types of acids, we have to remove the gen ending from the hydrogen and change the "ide" ending on the second element to "ic." So hydrogen chloride becomes hydrochloric acid. A compound must contain at least one ionizable hydrogen atom to be an acid upon dissolving. So here are some simple acids that you may have heard of before already. HF, hydrogen fluoride, becomes hydrofluoric acid. Hydrogen bromide becomes hydrobromic acid. Hydrogen cyanide becomes hydrocyanic acid. Organic compounds. Our nomenclature discussion so far has focused on inorganic compounds, generally defined as those without carbon. Organic compounds contain carbon and hydrogen, sometimes in combination with other atoms. Hydrocarbons contain only carbon and hydrogen. The simplest hydrocarbons are called alkanes. Here are the first 5 alkanes. We have methane, ethane, propane, butane, and pentane. You may probably be familiar with methane and propane from, say, grilling. You will notice that the chemical formulas are just carbons with hydrogens, and as the carbon increases, we name it accordingly. You may also notice that the carbons are always in a chain. They are always bonded to each other, and the hydrogens are more peripheral. As they get longer, we may notice that the names hexane, heptane, octane, nonane, and decane are starting to use Greek prefixes to describe how many carbons are in the molecule. So octane, for example, what you pump into your car as gasoline, has 8 carbons in the carbon chain. Many organic compounds contain groups of atoms known as functional groups, which often determine a molecule's reactivity. So for example, everyone's favorite alcohol has an OH, with oxygen-hydrogen bonded. Aldehyde has a carbon double bonded to an oxygen with a single hydrogen bond coming off the carbon. Carboxylic acid, a carbon double bonded to an oxygen with an alcohol coming off the carbon, is the main functional group in vinegar. It's the thing that makes it acidic. And finally, amines have a nitrogen with 2 bonds to hydrogen. You may be familiar with amines from, say, amino acids, which are a mixture of amine and carboxylic acid in the same molecule. Covalent bonding in ionic species. Polyatomic ions consist of a combination of 2 or more atoms. Formulas are determined following the same rules as for ionic compounds containing only monatomic ions. Ions must combine in a ratio that gives a neutral formula overall. So for example, calcium phosphate, calcium has a 2+ charge, and the phosphate, PO4 3-, the polyatomic ion, has a charge of 3-. Therefore, we're going to need 3 equivalents of calcium to give us a 6+ charge, and 2 equivalents of the phosphate to give us a 6- charge, to give us a overall formula of Ca3 PO4 2 in parentheses with a neutral charge. Here is a list of common polyatomic ions you need to be familiar with. And here's a continuation of that table. Oxoanions are polyatomic anions that contain 1 or more oxygen atoms and 1 atom, the central atom, of another element. Starting with the oxoanions that end in 8, we can name these ions as follows. The ion with 1 more oxygen atom than the 8 ion is called the per whatever 8 ion. Thus, ClO3- is the chlorate ion, so ClO4- is the perchlorate ion. The ion with one less oxygen atom than the ate ion is called the ite ion. Thus, ClO2- is the chlorite ion. The ion with two fewer oxygen atoms than the ate ion is called the hypo-ite ion. Thus, ClO- is the hypochlorite ion. At minimum, memorize the oxoanions that end in ate so you can apply these guidelines when necessary. So examples, as we said, chlorate, ClO3-, we have the perchlorate with ClO4-, chlorite with ClO2- and hypochlorite for ClO-. More common ones, nitrate, NO3-, you need to be familiar with nitrite, NO2-. Phosphate, PO4-3-, you need to be familiar with phosphite, PO3-3-. Sulfate, SO4-2-, becomes sulfite when you lose an oxygen, SO3-2-. Oxoacids. Oxoacids, when dissolved in water, produce hydrogen ions and the corresponding oxoanion. So an acid based on an ate ion is called something ic acid. So for example, with the chlorate, ClO3- becomes HClO3 chloric acid. An acid based on an ite ion is called something us acid. So HClO2 is chlorous acid. And prefixes and oxoanion names are retained in naming the oxoacids. So HCl4 is perchloric acid, and HClO is hypochlorous acid. Oxoacids can be monoprotic, with one ionizable hydrogen, or polyprotic, where more than one ionizable hydrogen is present. The names of the anions indicate the number of remaining hydrogens. So H3PO4 contains the phosphate ion, therefore it should be phosphoric acid. However, once we remove a proton, H2PO4-, we would say it's dihydrogen phosphate ion. HPO4-2- becomes hydrogen phosphate ion, and PO4-3- is just phosphate ion. Because there's a way to figure out the names of these ions if you know the ate, remembering all the names and formulas is greatly facilitated by memorizing just the common ions that end in ate. So know your chlorate, iodate, bromate, sulfate, phosphate, nitrate, carbonate, oxalate, chromate, and permanganate. Hydrates. A hydrate is a compound that has a specific number of water molecules within its solid structure. For example, in its normal state, copper 2 sulfate has 5 water molecules associated with it. So the systematic name, copper 2 sulfate pentahydrate, is used, and the formula would be CuSO4 5H2O. Some other hydrates are barium chloride dihydrate, lithium chloride monohydrate, magnesium sulfate heptahydrate, and strontium nitrate tetrahydrate. When the water molecules are driven off by heating, the resulting compound, copper sulfate, is sometimes called anhydrous copper 2 sulfate. Anhydrous means the compound no longer has water molecules associated with it. How can we visually tell? Well, copper sulfate anhydrous is white, whilst copper sulfate pentahydrate is blue. The water is coordinating with the metal, making it colorful. Familiar inorganic compounds. So some compounds are so common in our lives that we can call the common name as opposed to the systematic name. These include water, ammonia, dry ice, salt, laughing gas, marble, baking soda, Epsom salt, and milk of magnesia. Here you have their chemical formulas and their systematic names, if you were curious. Molecular and formula mass. The molecular mass is the mass in atomic mass units of an individual molecule. To calculate molecular mass, multiply the atomic mass for each element in a molecule by the number of atoms of that element and then total the masses. So the molecular mass of H2O is 2 hydrogens plus 1 oxygen. So 2 times 1.008 atomic mass units plus 16 atomic mass units gives you a total mass of 18.02 atomic mass units. Because the atomic masses on the periodic table are average atomic masses, the result of such a determination is an average molecular mass, sometimes referred to as the molecular weight. Although an ionic compound does not have a molecular mass, we can use its empirical formula to determine its formula mass, the mass of the formula unit, sometimes called the formula weight. The process is the same. To calculate formula mass, multiply the atomic mass for each element in a formula unit by the number of atoms of that element and then total the masses. Percent composition of compounds. A list of the percent by mass of each element in a compound is known as the compound's percent composition by mass. So the percent mass of an element is n times the atomic mass of the element divided by the molecular or formula mass of the compound times by 100, where n is the number of atoms of the element in a molecule or formula unit of the compound. So for example, with hydrogen peroxide, the percentage of hydrogen is 2 times the mass of hydrogen divided by the total molecular weight of hydrogen peroxide times by 100. And we'll notice that hydrogen is only 5.926% of the mass, whilst oxygen is 94.06% of the mass. If you're wondering why it doesn't add up to 100, well, that comes down to rounding and the fact that we are using average masses. We could also have used the empirical formula of hydrogen peroxide, HO, or HO, for the calculation. In this case, we could have used the empirical formula mass, the mass in AMU of one empirical formula, in place of the molecular formula. The empirical formula mass of H2O2 is 17.01 atomic mass units. So if you do the mass of hydrogen divided by the total mass of the empirical formula mass times by 100, we will also get our 5.926%. Whilst oxygen, we do 16 divided by 17.01 times by 100, gives us 94.06%. Molar mass. The molar mass, big M, of a substance is the mass in grams of 1 mole of the substance. The molar mass of an element is numerically equal to its atomic mass unit. So 1 mole of carbon is 12.01 grams because 1 carbon of atom is 12.01 atomic mass units. The molar mass of a compound is the sum of molar masses of the elements it contains. So 1 mole of water is 2 times the mass of hydrogen plus the mass of oxygen, giving us 18.02 grams. 1 mole of sodium chloride is the mass of sodium plus the mass of chloride to give us 58.44 grams. When expressing the molar mass of elements such as oxygen and hydrogen, we have to be careful to specify which form of the element we mean. For instance, the element oxygen exists predominantly as O2, but we might also mean atomic oxygen, O. We must consider the context to tell which form of the element O2 or O is intended. So context, for example, how many moles of oxygen react with 2 moles of hydrogen to produce water? Here we're clearly talking about oxygen molecules, i.e. the gas O2, therefore the molar mass would be 32 grams. However, if we say how many moles of oxygen are there in 1 mole of water, we know that oxygen in water is O, so we must use O, and the molar mass will be 16 grams. If we're talking about air, it's approximately 21% oxygen. Once again, we're talking about the molecule oxygen, O2. Whilst many organic compounds contain oxygen, it's part of the molecule, it must be O. Interconverting mass, moles, and number of particles. Well, this must look really familiar to you. We need to be able to convert mass to moles and moles to the number of particles, which now are not just atoms, but also molecules, ions, and formula units. You need to be able to interconvert between all these values because depending on the context of any question, you may have to use one, but you are given another. Determination of empirical formula and molecular formula from percent composition. Using the concepts of the mole and molar mass, we can now use an experimentally determined percent composition to determine the empirical and/or molecular formula. The empirical formula gives only the ratio of atoms in a molecule, so there may be multiple compounds with the same empirical formula. If we know the approximate molar mass of the compound, we can determine the molecular formula by dividing the molar mass by the empirical formula mass. We then multiply the empirical formula by this number to obtain the molecular formula.